It's complex numbers. So first question, if a is less than 0, b is less than 0, then square root of a times square root of b is equal to. So the definition goes something like this, that square root of any negative number, say you have square root of negative 3, this thing can be written as square root of 3 into square root of negative 1, and we have defined square root of negative 1 to be iota. So square root of negative 1 cannot be negative iota, right? Does that make sense? So here the positive and negative thing does not make sense, because iota in itself, we don't know if it's positive or negative, or what even is this. It's actually imaginary. We have created a number ourselves, so we have defined square root of negative 1 to be equal to iota, and that's it. So according to our definition, we can say square root of a, which can be written as square root of negative a times negative 1. So this is a positive number, so this can be written as square root of negative a into square root of negative 1, and square root of b can similarly be written as square root of negative b times square root of negative 1, and this thing will be iota, and this thing will also be iota. So this is going to be square root of negative a negative b, which is positive ab times iota squared. So that will be negative 1, so negative square root of ab. Yeah, that makes sense. Okay, so over here they have done it a little differently. So they have this mod and stuff over there. Okay, so now what? So you want to use mod, right? Okay, we can do that as well. So instead of writing negative a over here, I will just write mod a, and that times negative 1. So over here you will just have mod over here. So when you will multiply this, it's going to be negative mod a b. Yeah, that makes sense, I guess. Alright, so this thing can be written as square root of mod a b times square root of negative 1 times I. So it's just gonna be, yeah, times actually negative 1 over here, because iota squared is negative 1, and that times iota, I guess. Does that make sense? Well, I know it's gonna be negative 1, and then just got to have that iota over there. So yeah, well, then this should be equal to, alright, this is not making sense right now. Oh, no problem, no problem. So the problem with this kind of definition is that, so yeah, the square root, it can be just modified to give two different answers, and that's the problem. So our original answer that we got was negative square root of ab, right? More like negative square root of minus a into minus b, and that can be written as negative square root of mod a times mod b. But then mod b, instead of writing all that, I will just write negative b. Yeah, that makes sense. So it's going to be negative square root of mod a b, and then square root of negative 1 is just iota. So the good thing is that negative iota, right? What can I say about negative iota though? Square root of mod a b, then can negative iota be written as iota? No, that's not correct. That's weird. So yeah, it's gonna be none in that case. Huh, was not expecting this. Hey, no, that should not be the thing. Well, let's see. So what would square root of mod a times b be? So it's gonna be square root of a b times negative 1, right? And that thing times iota, so this would be square root of ab times iota, which is like iota squared. So that would be negative square root of ab as well. So in both cases we get the same thing, but then why can't I convert this thing into that thing directly? So so I can definitely write as mod a. Oh, okay, that's weird. So I should have written it as mod a upon minus. Okay, that's really weird. So this should be negative 1 upon iota square root of mod a times b, which, yes, is iota times square root of mod a times b. Yeah, that that is weird. So the problem is that if you have negative 1 on the denominator, you can write it differently, and if you have negative 1 on the numerator, you can write it differently as well. So it's kind of a complicated situation, but I guess we just have to go in the numerator way. So writing it in the numerator for the negative numbers, and yeah, whatever. It's not really useful. I mean, this question, it's not using any actual facts. It's just definitions, which are confusing most of the time. Next question. If a squared plus b squared equal to 1, then 1 plus b plus I a upon 1 plus b minus iota a equals to. Come on, no big deal. So just multiply by the conjugate. So it's going to be 1 plus b plus ia squared upon 1 plus b squared minus ia, that thing squared. So that's just going to be negative 1 times a squared, so positive. So it should be 1 plus b. I guess there must be some other way as well. 1 plus b, you say, huh? What about I go for... No, that won't quite work. So I just gotta do this thing. So yeah, 1 plus b plus iota a squared. What would that be? That will be 1 plus b squared plus 2a into 1 plus b iota plus, so minus actually, because iota squared is negative, so negative iota, negative a squared upon 1 plus b squared plus a squared. Cool. And we have a squared plus b squared equal to 1. So this upon expansion, let's just actually write this. So it should be equal to b squared plus 2b plus minus a squared plus 1 plus 2a plus 2b iota upon... Is there really no other way for this? There must be, right? Hey, just wait a second. 1 plus b plus... Okay, that is not nice. Well, whatever. If they had multiplied this thing, then that would be, I guess, a little easier. We can write it as a square as well, in fact. Yeah, so we can write a squared plus b squared as a plus ib into... Okay, that's not useful. Yeah, that's not useful. Gotta do something else. 1 plus iota b. Whatever. Just do this thing then. Upon... Where was I? This thing. So b squared plus a squared plus 2b plus 1. Okay, so this thing is just 1. So I can write it as 1 over there. So it's just going to be upon 2 plus 2b. And let's just start writing everything in terms of b, because that's what we have. So minus a squared. 1 minus a squared, that's just b squared. So yeah, it's going to be 2b squared plus 2b plus 2a plus 2b times iota. So what's that gonna be? 2 everywhere, it just cancels. Just got 1 over here. Okay, then what? Then it can be written as 1 plus b, like b plus a plus b upon 1 plus b. Okay, that's not nice. Times a. Hey, was that thing really? No, it was having ab over here, right? ab over there should be his thing. Oh, this thing is just a in that case, so a iota. So it's gonna be b plus a iota. Okay, so this should be the answer. Next question. The center of a regular hexagon is at origin and one of the vertices on... So this argand thing, whatever this thing, it just refers to a complex plane. Yeah, if the center of a regular hexagon is at the origin, okay, so say you just got a regular hexagon like this. The center is at the origin. Its vertices, one of the vertices is 1 plus 2 iota, then its perimeter is... So no big deal, just find what this distance is going to be. So it's going to be square root of 1 squared plus 2 squared, which is... What's the square root of 5? Yeah, so that's this distance. Now I just need to find the perimeter. We know this distance is exactly equal to this distance, so it's just going to be 6 square root of 5. Easy. Next question. The principal argument of the complex number 1 plus iota power 5, 1 plus square root of 3 iota power 2. Alright, no big deal. So 1 plus iota power 5, we can write it as square root 2 times 1 upon square root 2 plus 1 upon square root 2 iota stuff. So it's just going to be square root of 2. It's cosine of pi by 4, it's sine of pi by 4. So it's e power iota pi by 4. So from the Euler's theorem. Yeah, so it's going to be e that times 2. So it's going to be e to the power of negative, sorry, e to the power I pi by 2 over here. Then for this thing, it's just going to be e to the power of, so cosines like 1 by 2. It's going to be pi by 3. So that times 2. Hey, wait a second. This should be 5 over there. So it's going to be 5 pi by 4 actually. It's 5 pi by 4. For this thing, it was going to be 2 pi by 3. So I 2 pi by 3. And everything else is just a constant, a big real number over here. We don't care about that. We just care about the e to the iota thing. Upon minus 2 iota. So iota itself, right? So it's gonna be when sine is 1, cosine is 0. So that's pi by 2, I guess. So e to the power of I pi by 2. And then there are like negative numbers. Okay, that's not nice. We don't want negative things. Okay, so this negative we can write as positive. So square root of 3 and minus 1, square root of 3 by 2 and minus 1 by 2. So that is when sine is negative 1 by 2. So going to be negative 30 degrees, negative pi by 6. So e to the power of I pi by 6. Yeah, that makes sense. Okay, so it's going to be e to the power of I 5 pi by 4 plus 2 pi by 3 minus pi by 2 minus pi by 6. Let's see what can we do with this thing. So 4 minus 3 is like 1. 3 pi by 6 over there. Oh, that completely cancels as well, so that's nice. This thing completely cancels. It's going to be e to the power of I 5 pi by 4. So 5 pi by 4 will be our argument, and this number will be positive, so nice. Wait a second, 5 pi by 4, yeah, right? Is it wrong in any way? Oh, it should be minus over there. Right. It should be minus over there, so it's going to be plus. Okay, fine. So pi by 4 plus 2 times of pi by 6, which is pi by 3. Alright, so it's going to be 15 plus 4. Does that look correct? Yeah. So 15 plus 4 is 19.12 pi. This one. Next question. If iota squared equal to negative 1, then the value of summation from 1 to 200 of iota power n is. So yeah, that's nice. So we need some kind of recursive pattern. So first of all, 1 plus iota plus, well, so the next thing will be negative 1 plus negative iota. Nice, very nice. So this cancels. So and the next one will be, well, now we got negative iota, that times iota is going to be 1, and then once again plus iota. So whenever you got something like this, sum of 4 of these terms is just going to cancel. It's going to become 0. So 1 to 200, you got 200 terms which are multiples of 4, and we are starting with iota power 1. Oh, that's not nice. We don't want to be starting with iota power 1. We want to be starting with 1, so I'm gonna add 1. Alright, so summation from n equals to 0 to 200, does that make sense? Iota power n, well, that would be 1 plus iota plus all that stuff, right? But now you got 201 terms, so the last term, it won't get cancelled. And what's the last one gonna be? It's gonna be iota power 201, sorry, 200, just iota power 200, which is like negative 1 power 100, so it's going to be 1 in that case, huh? Okay, not bad. So this would be 1, but then this n equals to 0 term is actually not there, so it's just going to be 0. What? Alright, okay, huh, not bad. I mean, like, that cancels as well, huh? So what you mean is that iota, and then you got negative iota. Yeah, obviously, come on, this is the same thing, it's gonna cancel anyway, so That's nice. So it's just gonna be 0. Next question. The complex number 2 power n upon 1 minus iota to the power of 2n plus 1 plus iota to the power of 2n, okay, is equal to. So let's figure out what this complex number is. Euler's theorem? Yeah, that's what we use most of the times, but no, not really. So I'm gonna do it some other way maybe. Yeah, multiply by the conjugate. So that will be doing it. So 2 power n 1 plus iota to the power of 2n 1 minus iota power of 2n times 1 plus iota. So it's just gonna be 1 squared minus iota squared, which is 1 plus 1, which is 2. So 2 power 2n. Okay, so 2 power 2n. Well, I wasn't expecting this thing. This is gonna be 2 power 2n minus n over there, right? Yeah. So this is upon 2 power n over there. And for that guy, well, it's already in the format, so why even bother? It's just gonna be 2 times of that. So 1 plus iota to the power of 2n, right? Upon to the power of n minus 1. Well, alright, that's weird. Did I miss something? Upon 2 to the power of n upon it should be the same thing, right? Multiply by the conjugate. 1 square. Yeah, it should be 2. It's gotta work, right? 1 plus iota. Come on, yeah. So which of these options then? Well, 1 plus negative 1 to the power of n times iota power n. Alright. Okay. How? Iota power n. So negative 1 power n. Just how do you even do that? So it's everything in terms of n over there. So maybe we should be writing this in terms of n as well. So first of all, 2 times of all of that. So 2 times, well, square this. So just get 1 squared, and then iota squared is negative 1. Well, that completely cancels, just 0. And okay, upon 2 power n. Okay, so this completely cancels. So sorry, this cancels. It's still there. So 2 into iota power n. Alright. So can this thing also be written as 2 into iota power n? Well, negative 1 power n. It's either 0 or it's 1. When is it 0? I don't think it's 0 at any time. Well, we'll just square that. So 2 power n upon this thing squared, that would be negative 2 iota to the power of n. Okay, so this cancels. So it's gonna be 1 upon negative iota power n. So like negative 1 power n iota power n. Plus, well, this over here is the same as saying negative 1 power n and iota power negative n. Plus, so similarly for that, but it's just going to be the opposite one. So it's negative 1 power n over there too, and iota power positive n this time. Yeah. Next what? So gonna multiplies by iota power n, I guess. Wait a second. No. Oh, that's not the thing. It should be positive 1 power. Right. It's not even there. In fact, that's gone. This is also gone. Now what? So now multiply this by, well, let's say iota power positive n. No, that won't work. That will work. Negative 1 power n and by iota power negative n. So this will be negative 1 power negative n, I guess. Okay, upon iota power negative n. So that just times iota power n in that case, plus iota power n. This thing is just negative 1 to some 2n power, which is a positive quantity. So this is going to be 2 iota power n. So yeah, that is our answer in any way. So we just want to show that this thing is supposed to that. Well, okay, it's either 0 or it's 2 into I power n. How can it be 0 though? Well, how can it be 0? I don't think so. So okay, come on, think. At about n, that's only over there, so it's gonna be none of these. Okay, this does not look correct, because why would have they given us this thing if it was supposed to be none of these? Is this not going to work? Do we not have a generalization? Come on. I used to think that complex numbers are doable, but it's not doable. I don't know. Move on. Number of real value of theta for which the expression is a real number. Okay, this expression is a real number. Fine. So multiply by the conjugate. 1 plus iota cosine theta upon. So the conjugate will be 1 plus 2i cosine theta. Over here, just gonna get 1 squared 1 minus 2, so like plus, okay, plus 4 cosine squared, okay, minus 4i cosine theta. Cool. So 1 minus 2 cosine squared theta plus, it's gonna be 2i cosine theta. I cosine theta is 3i cosine theta. So we want this to be a real number. In that case, this thing must be 0. Doesn't matter what this thing is. So we just want cosine theta to be 0. Nice. So our theta must be pi by 2. Well, not pi by 2. And 2n plus 1 into pi by 2. That's when it is 0, right? But are we making some big assumptions? Value of theta in. Okay. In fact, since we just want that, just find all the values and try to put them. So wait, no, minus 2, but that's going to be 8 values. That's not 8 values. One circle 2 values, two circle 4 values. Okay, let's just try them. Right, so say you try minus pi by 2 and pi by 2. What do we get for that? Okay, gonna put minus pi by 2 over there, so it's gonna be 1. Well, that's 0. Okay, so 1 upon 1. Yeah, I should have expected it. Yeah, it's gonna work. That's the only way it works, and that will always work. That's nice. So there are going to be 4 values. Next question. 4 values. So start from minus 2 pi and go full circle. You do get cosine equals to 0 just 2 times. So yeah, 4 values. Number of pairs xy for which the equation is satisfied. Okay, x power 4 plus 2xi minus 3x squared plus yi equals to 3 minus. Wow, I was not expecting this thing. Okay, so first of all, writing in standard form. So it's gonna be x power 4 minus 3x squared plus iota times, so 2x minus y equals to 3 plus 1 4. Okay, plus 2y minus 5 iota. So we should have this equal to that. So because x, y are real numbers, so it's going to be 2x minus y equal to 2y minus 5. So that gives 3y equal to 2x plus 5. Our first equation. And what's the other equation that we have? We have x power 4 minus 3x squared equal to 4, which means x power 4. Is that the thing? Yeah, it is. X power 4 is 3x squared minus 4 equals to 0. Well, minus 4 is minus 4 into 1. So x power 4 minus 4 into x plus 1 equals to 0. So x squared, everywhere it should be x squared over there, equals to 0. Well, it's real numbers, so this is discarded. X squared equal to 4, so x equal to plus minus 2. That's the solution. At the same time, this should also be satisfied, so just put this over there. So 3y equal to 5 plus minus 4, which is 1 or 9. So y is 1 by 3 or 3, right? So for x equal to 2, you have 3, so it's going to be 2 comma 3, and for minus 2 you just have 1 by 3, so minus 2 comma 1 by 3. That's gonna work. So number of pairs 2. Next question. Am I missing something? No, I'm not. Next question. if the conjugate of x plus iy into 1 minus 2i be 1 plus I, then all right, the conjugate of this thing be 1 plus I, then right, just multiplying by that will give us yeah, whatever, don't even worry about this, just multiply this thing first. So it's gonna be x minus, well, so minus minus is plus 2y plus iota times, so minus 2 times x minus 2x and y times 1 plus y. So its conjugate, that will be x plus 2y plus 2x minus y iota. This thing is equal to 1 plus iota. That's what they're saying. So this is equal to 1, this is equal to 1. Where does that happen? X plus 2y equal to 1, 2x minus y equal to 1 as well. Subtract. So subtracting, you will, no, don't do that, multiply by 2. So add, so just get 5x equal to 3, x equal to 3 by 5. Okay, just put that over there. So x 2y equal to 1 minus 3 by 5, which is 2 by 5. So y equals to 1 by 5, right? So x equal to 1 by 5, no. X equal to 1 by 3, no. X plus iy equals to 1 minus, I mean, yeah, that makes sense. This guy's conjugate is that, which means this guy's conjugate is that as well, right? So it's gonna be this thing, sure. And well, yeah, so this guy's conjugate, what will that be? It's just gonna be x minus iy and 1 plus 2y. So yeah, this, wait, 1 minus, no, not gonna work, because 1 minus I, that's not what we want. That's not what we want. It should be 1 plus I. Yeah, so this is the only correct option. Next question. The complex numbers sine x plus I cosine of 2x and cosine x minus I sine of 2x are conjugate to each other for x equal to, come on, these are conjugates to each other. So just got sine x equal to cosine x and cosine 2x equal to sine 2x, right? So negative of negative positive, yeah, that makes sense. So it's just going to be tan 2x equal to 1 and tan x equal to 1 as well. Well, if tan x is 1, tan 2x, which is 2 into 1 upon 1 minus, wait, oh no, that doesn't make sense. Shit, tan 2x won't be making sense if tan x is 1, so this cannot be happening. There's no value, there's no such value that this can be happening though. I mean, okay, this will give like x equals to pi by 4 plus n pi, but then 2 times of that is like pi by 2 plus n pi, so that's gonna give either not defined or 0, which, and none of them are 1, so it's just not gonna happen. These cannot be conjugates. Next question. The real part of 1 minus cosine theta plus 2i sine theta power negative 1 is, wow, let's do it. So 1 minus cosine theta plus 2i sine theta, the real part, can we just kind of yeah, let's take 2 common, and then that will give like cosine squared over there. That's not a nice idea. Sine squared, and it's gonna give 2 sine cosine. Well, maybe you can take out that cosine from there, which is a real thing. So from that you get something like a cosine I sine format, so maybe it will work. So let's take 2 common, and everything is in power negative 1. So 1 minus cosine upon 2, that is just sine squared of theta by 2, okay, plus that 2 is gone, but yeah, this thing can be written as 2 sine theta by 2 cosine theta by 2 iota. Well, it's not working, it's just not working. Now what? It should be 4 over there. Well, that's not nice. So now what? I don't want to be multiplied by its conjugate though. That will be tedious. But we have to. There's just no other way. What happened? Nothing. Okay, just multiply by its conjugate. Is there some other easy way to do this? Yeah, whatever. Next, let's just do it. So 1 minus cosine minus 2 sine I multiply by that, and over here you're just gonna get minus cosine squared minus plus, so plus 2 sine squared. This thing is just, well, just that much. So the real part, so it's gonna be this thing, 1 minus c upon, okay, 2s squared, you say. Yeah, we can take 1 minus c common, so 1 minus c plus 2, so s squared is just 1 minus c squared, so 1 minus c into 1 plus c, so it's going to be 2 into 1 plus c, which is 2 plus 2c over there, cancels. Just got this as the real part, so 1 upon 3 plus c as the real part. Wait, what? Is that the case? Oh no, it should be 4 because 2 squared, so 4 over there. It should be 5 in that case, so 5 plus 3c. Next, if alpha and beta are different complex numbers with beta equal to 1, then beta minus alpha upon 1 as conjugate of alpha, so beta is equals to, okay, mod beta is 1, alpha beta are two complex numbers. What can we say? Mod beta is 1. Well, then beta is just e to the power of negative b, say. Why am I writing this thing? E power e power iota b. What am I writing? Okay, and you don't know anything about alpha though. The alpha is just something like r e to the power of I a. So then conjugate of alpha, that will be r e power minus I a. Just going to put that over here. So beta, which is e power I beta minus alpha, which is r e power minus I alpha. Maybe it's not such a good idea. Still, let's try it. Upon, probably you can just take e power I common, and that's why it's a good idea. Upon 1 minus, so conjugate of, it's going to be r e power, minus, no, it's not minus over there, it's only minus over here as well. That's I a e power I b, so that's nice. So now what? This thing is equal to, so the mod of that. Okay, how do we even calculate this thing? E power I e power I, wait, no, but we don't know what happens when theta equals to 1. That's not a nice quantity, right? So that's not going to be called calculatable. God, there must be some other way then. Yeah, there is. Yeah, it's actually not that bad. It's going to be the conjugate of that. Not bad at all. So we don't even need all that stuff. So beta minus alpha upon, multiply this thing by the conjugate of beta. Since we just want a mod of this thing, so it does not change it, so it's still going to be the same thing. So beta minus alpha upon this thing minus, so beta and mod beta times conjugate of beta. What will that be? That is gonna give us 1, because yeah, mod beta is 1. So this thing, so let's say beta minus alpha is some quantity x, so it's going to be x upon x conjugate. We don't care what x is. So this is, looks like I've seen this somewhere. So say it's r into e power I theta, so we can write it as r e power I theta upon r e power minus I theta. So this gets cancelled, and the mod of that thing, that's just 1, because it's just going to be cosine plus I sine, something like that. So yeah, it's going to be 1. Next, amplitude of 1 plus I upon 1 minus I upon 1 plus I is, they are conjugates, right? Wait, we want amplitude. Okay, does that mean the argument? Okay, So that doesn't mean the mod. What does that mean? I guess it does mean the argument. So let's do this. What's the argument of this thing? Uh, yeah, well, 1 upon square root 2 minus 1 upon square root 2 iota upon 1 upon square root 2 minus plus 1 upon square root 2 iota. This thing is just e power, well, it's a cosine of pi by 4, and no, it should be cosine of minus pi by 4. That will suit better. So minus pi by 4 I, right? So minus pi by 2. Nice. Next, if mod of z1 equals to mod of z2 and amplitude of z1 plus amplitude of z2 equals to 0, then wait, what? How can they be 0? Amplitude has, oh, amplitude, why am I, amplitude does not mean the mod, right? It means the argument. So okay, their magnitudes are equal and their amplitudes are inverse, which means they are conjugates basically. Then, well, yeah, they're conjugates of each other. Z1 equals to z, yep, z1 plus z2, no, that's not correct. Next, amplitude of sine pi by 5 plus I into 1 minus cosine pi by 5. All right, so now we can take some stuff common. So first of all, I will write it as 2 sine of pi by 10 cosine of pi by 10 plus 2 sine squared of pi by 10 iota, and then let's just take 2 sine of pi by 10 common. So now it's cosine of pi by 10 plus sine of pi by 10 iota. So this thing is some real number, so that doesn't count in the argument. This does, right? This does. So yeah, pi by 10, that's going to be the argument. So next question, magnitude is 4 and argument is 5 pi by 6 g. Okay, what's this thing? I don't know. Okay, then I don't know what this question wants to say. Next question, the square root of 3 minus 4 iota r, right? So square roots, that's what they mean, I guess. So we just got z squared equal to 3 minus 4 iota. Say z is a plus b iota, then squaring this you will just get a squared minus b squared plus 2ab iota equal to 3 minus 4 iota. So a squared minus b squared equal to 3 and 2ab equal to minus 4. Does that make sense? It does. So ab equals to minus 2 and a squared minus b squared equal to 3. So say a is, in fact say b is minus 2 upon a, so put that over there. So it's going to be a squared minus b squared, which is just 4 upon a squared equal to 3. So a power 4 minus 3a squared minus 4 equal to 0. So just get a squared minus 4 into a squared plus 1 equals to 0. Cancels because a is a real number, and just got a equals to plus minus 2, which gives b equal to, in that order, minus plus 1. Yep. So 2 comma minus 1, the AB order pair is 2 comma minus 1 or minus 2 comma plus 1. So our root, which is z, that should be 2 minus iota, okay, or minus 2 plus iota. So basically plus minus of 2 minus iota. Alright, this works. Next question, real part of e power I. Wow, okay, fine. So e power, well, this quantity, is that what they want us to do? First of all, do we have to do this first? I guess, yeah, that's what we do with power towers, right? Yeah, pretty sure that's what they want us to do. So e power I theta is just cosine theta plus I sine theta. So just e power cosine theta times e power I sine theta. It's gonna get ugly. So e power cosine theta times, so this thing can be written as cosine of sine theta, okay, plus I sine of sine theta. So the real part is whatever this number is. This should be e power cosine theta times cosine of sine theta. Wow. So these won't work. E power cosine theta, cosine of sine theta should be the thing. Next question. In algebraic form, z equal to I power I simplifies to, okay, I power I. What do we know? E power, well, okay, first of all, you should write I somehow. It's when sine is 1 and cosine is 0, which happens at pi by 2. So iota is just e power pi by 2. It's going to be e power pi by 2 iota. Yeah, that's I basically. That to the power of I, so it's going to be e to the power of negative pi by 2. Well, that was easy, really easy. So this just simplifies to e power negative pi by 2. Easy. Next question. E power 2x plus 1 upon, okay, equals 2. Oh, so do we need to check all of these options? That I don't think we should be doing. Okay, what can we do? E power 2x. Come on, think. Hey, I've seen this question once. Yeah, I've seen this somewhere. So I know that e power I theta is cosine theta plus I sine theta, right? And we also know e power negative I theta equals to cosine theta minus I sine theta. Adding them, we just get cosine theta equal to e to the, what do we have? E to the I theta plus e to the minus I theta upon 2. So when you put cosine of I theta, that's going to be e power minus theta plus e power theta upon 2. This is like the well-known cosine h function, but that's not really important over here. Similarly, you can also write, basically subtract them and take half and divide by I as well. So sine theta is just e power theta minus I theta minus e power minus I theta upon 2I. Alright, so sine of I theta, that should be e power negative theta minus e power positive theta upon 2I, which is, yeah, so I upon 2 into, well, iota into e power theta minus e power minus theta upon 2. That's nice. And we can do some kind of similar stuff for there as well. So over here, just got e power x minus e power minus x, right? Yeah, upon 2, that times I upon, so everything like that, upon e power x plus e power minus x upon 2. That's nice. So this thing is just sine of I x upon cosine of ix, which is tan of ix, right? Yeah, that's the thing. Okay, so that's it. Let's check this. A is correct. 19C. Alright, this I was not able to do. I don't know what this question was. 15th, right? 15th C. Yeah. 14th B. 13A. 12th C. 11th C. Wait, what? 11th C. It's not D. Minus 5%. Alright, I don't know. Yeah, this is wrong, and this should be the correct answer. Okay, 10th D. 9th C. 8 C D. C, and yeah, none of these, as I expected. It should be this thing. So I don't know I should give correct or not. I guess I didn't have the courage to do that. Anyway, the next question. Fifth C, okay, D. C, that's not what I wanted, so it should be this thing. Wait, the principal. All right. The principal argument. That makes sense. Yeah, I guess I need to rate something more. So 19 pi by 12. That's not the principal argument. That's what you're saying. I guess like it should be in the domain of sine inverse maybe, because they did have this negative stuff over there. So 19 pi by 12, it's something like pi plus 5 pi by 12, so over here. So this thing can be written as minus 5 okay, that doesn't make sense. Minus 5 pi by 12, that is weird. How is that the principal argument? So 2 pi minus, okay, 2 pi plus, no, minus 2 pi. So 19 pi by 12 minus 2 pi. 19 minus 24 pi upon 12, which is, yeah, it's minus 5 by 12. Okay, well, what can I say about this? 19 pi by 5 pi by pi plus 5 pi by 12, that's for sure. But then how is this equal to, how can it land over there? It's not the same thing as that, so it should be going like this, right? Is this actually bigger than, wait, but it's minus 5 pi, it's smaller than pi by 2, so then how can it even go over there? Is this like, okay, so 12 and then, oh right, so this can be written as pi plus 7 pi by 12, and guess what, 7 pi by 12 is actually bigger than pi by 2, so this thing should be over here. And then yeah, it's gonna be minus 5 by 12, so cool. All right, next 3 2 1 DCB. DCB. Yeah, that's it. I'm gonna stop now. See you later.